Morning. Thursday already. I'm like, I can't keep up. So just a quick review of what we talked about last day. We were talking about confidence intervals. And then I left you with a task of trying to interpret that interval that we built. So I'll bring that back in and we can talk about it. So just a quick review on confidence intervals. It was just 2 days ago. So I'm stockpiling another assignment. I'll see if maybe I'll break it up into 2 parts. So there'll be a confidence interval focused one, and then a hypothesis testing focused one. But there's a lot of overlap, as you'll see today. So I'm not sure if I'll be able to do that. I'll try, but because I know kind of more assignments is better, taking one big one and breaking it into 2, right? But so I'll try to do that, but see what I can pull off. Yeah, you'll see there's a lot of kind of layering that's going on today. So, all right. In terms of review, right, we talked about confidence intervals. Or we'll call them CI, confidential informants. And what is a confidence interval? Well, we take some point estimate, right? And so that would be our sample proportion, and later it's going to be our sample mean, right? So we take our best guess at whatever the thing is that we're trying to learn about, right? Whether that's a population proportion or a population mean, or later even a difference in population proportions or a difference in population means, right? So there's going to be a lot of scenarios that we can talk about. But the idea behind the confidence interval and later hypothesis testing is going to be the same. So a confidence interval in general is going to be a point estimate and that could be maybe p hat, right? The sample proportion. I leave it kind of, I'm putting it underneath because it could be something else. So in general, it's always going to be a point estimate. And then what we said was, okay, well, that point estimate is not going to be exactly what the population parameter is that we're trying to learn about. So then we build a little buffer around that point estimate. So we say plus minus, and we built it out and we said, okay, we're going to have some central 95% or central 90% or 99%. And so we're going to have this critical value, which we denote by Z star. So Z star, this is a critical value. Critical value. And this is the only thing that dictates the confidence level. So this is dictates the confidence level. Right. And we said, okay, well, we know we have the tools to be able to figure out what these things are, what the critical values should be. Just by using the Z table, we can find, okay, if I want the central, something weird, maybe 97.5%, then I can find the central 97.5, and then I have 2.5 split between the 2 tails. So now I'm at 1.25 in the tail, and then I can find a Z score that corresponds to that. We have those tools, but we're not going to do that, right? What we said was, okay, the critical value is going to come from the T table, table C in the set of tables that I gave you, right? And so we said the critical value is going to come from this table, and I'll bring it in here. And what we said was, okay, we're going to ignore the midsection for just a little bit. Right? So ignoring all of this, blah, 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 and we'll get there. But down here, we see there's a Z star, okay? And so what we do is we just kind of trace down to the bottom to find our Z star. Let me see if I can line these up sort of here. Good enough. Okay, and so we have kind of dot, 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 so on and so forth. Okay, and so the critical values come from here. So if I want to build a 98% confidence interval, then I need to use a critical value of 2.326. So from here on out, if you're building a confidence interval, right, 95% confidence interval, for example, then you have to use 1.96. If you use that rough approximation of 2, you're not going to get quite the right values and it's going to mark it wrong. Okay, so just make sure that you're using these confidence levels. And actually before, because I want to refer to this table a couple more times, so maybe what I'll do is I'll erase this just temporarily. And then I'm gonna just copy this and put it down. I've got a stockpile down here. Scroll it away. Now I'll put that line back. Okay. So that's where we're going to get our critical value from. Okay. And then we need to multiply by the standard error of the point estimate. So times the standard error of the point estimate. Which for a sample proportion, the standard error of p hat is the square root of p hat times 1 minus p hat over n. Now, the standard error calculation is going to change with the point estimate, right? So when I give you the, when we want to try to approximate the population mean, then of course our point estimate is going to be our sample mean because that's our best guess at what it might be. And then I'll tell you what the standard error of X bar is, right? So you'll have those components and your job is to put them together into a confidence interval. Okay, so the general format always stays the same. And so that's important to remember. Okay. Let me go back to last day. Oh yeah. Oh yeah. We also talked about how to report the interval. We have to use round brackets and you want to go from the lower bound comma up to the upper bound. And so order is going to be really important, right? Because the interval from 2 to 4 exists, right? You have to imagine starting on your number line 2 to 4 exists, but 4 to 2 doesn't exist, right? And so even though that seems silly, I will take marks off if you have it in the wrong order because it doesn't make sense. Okay, I know that'll make you listen up. Yee. Taking marks off? Come on. So from last day, let's see here. I'm just going to copy. I'll copy this all. You have it, so. But I just want to bring it into paste. And I think, oh, come on. I'm going to try to make it a little bit smaller. So from last day, we had this. Okay, so we found our confidence interval, so we built our confidence interval, and of course, how we report the interval is important, but we also need to interpret the interval. So to interpret, I'll remind you how to interpret any interval in general. Okay, so to interpret a confidence interval in general, we use a standard blurb. Now, once you get more comfortable, you can use variations of this blurb, but it's going to be really important that you don't misstep. So in the beginning, I just want you to use this exact blurb until you feel more comfortable interpreting it, right? And so have this standard blurb, maybe write it on a Post-it note somewhere, and just kind of have it, and then you can fill in the blanks, and that's what I want you to do, okay? Because until you understand the concept behind it, it's really easy to misinterpret the confidence interval, and I don't want you to do that. I don't want to build any bad habits here. I just want to give you this standard blurb that you can always apply, and you'll know it's right? And then one day you'll be writing it and you'll say, oh, yeah, of course, right? But until that point, right? And it's not going to maybe feel obvious right away, but until that point, just keep working through the same blurb and using the same blurb, okay? So to interpret a confidence interval in general, we say something like, and maybe I'll use this blurb. So I usually start with we. I use the royal we. We are 95% confident or 90% confident or some blank percentage confident, depending on what interval you built, right? And so we are blank percent confident that the interval from blank to blank, okay, that's where you're going to pull the lower and the upper. All right, so here I'll say this is the lower bound, and this is up to your upper bound, of course. So we're blank percent confident, maybe potentially. The default is going to be 95%, but I'll tell you, construct a 90% confidence interval, construct a 95% confidence interval. So that's going to depend on the question. But we're 95% confident, for example, that the interval from, well, in this case, 0.8674 to 0.9066 captures, and that's going to be a key word, okay? Captures, we'll talk about why, captures the true proportion, okay? What I'm getting at is we're trying to capture the population proportion. We know everything about the sample proportion, and so one of the biggest mistakes that I see is you try to talk about the sample proportion, but you've built your interval around the sample proportion, and so of course it's in the interval because it's always in the interval because it's in the middle, right? And so the idea behind a confidence interval is you use your sample information and you're trying to capture the population proportion in this case. We don't know what it is, but we're 95% confident that we have captured it, okay? There's a 5% chance that we haven't, but we're okay with that, okay? That's the trade-off. So we're 95% confident that the interval from the lower to the upper captures the true parameter. Now remember, parameter is from the population, or maybe I'll say the true population parameter. Okay. Now, population parameter is kind of redundant, but I'm emphasizing that it has to be the population. And so one thing to remember, and so that's our standard blurb that we're going to use. So when I say something like the true population, we will never know what the parameter is, right? What the population is, but there is some true population proportion, for example, out there. If in theory we were able to select everyone and we were able to calculate the actual population proportion that exists, we just don't know what it is, and that's okay, right? So we will never know what this value is. Right. That's why it's so important to say that we're 95% confident that we've captured it. Okay. Which is why we say we are 95% or whatever percent maybe I'll say blank percent confident we have captured it. Okay. It's some fixed thing, but we don't know what it is. That's our whole goal of inference, is trying to figure out what it might reasonably be. All right. So in terms of this interval here, okay, one thing to remember about proportions especially is that a proportion is a percentage, right? If I just multiply it by 100. So often when we're talking about proportions, we're going to report them as percentages, because if you say 0.8674, although people are able to make that calculation, multiply by 100 fairly easily, it's still not a nice way to report information if you're trying to get information across quickly. So instead, often we report proportions as percentages. We often report proportions as percentages. You can see how that, as percentages. You can see how that would get confusing, right? We're 95% confident that the interval from 86.7% to 90.7%, these are two different, very different percentages, right? The 95% and the interval. So the context is going to be really important, and that's going to guide you to what makes sense here. So we are going to report the proportions as percentages unless it says otherwise. So we often report proportions as percentages, and usually one decimal place is good. Usually one decimal place is fine. Well, I've got room for fine. I was going to say sufficient. Maybe what I'll do is that depends, right? The 1%, yeah, you can use it as a guideline. Keeps resizing. There will be cases where, you know, you're talking about maybe a really, really small percentage. Then of course you'd want to increase your decimal places. But when we're talking about things like 86.74 and 90.66, that's just as well reported as 86.7 and 90.7, right? And so it depends on how close these values are to each other, right? You want to show that there is some distance between the two, so that's going to dictate the number of decimal places, but usually 1 decimal place is fine for these. And it'll say what decimal places to use. So to interpret this interval that we built last day, right? So we had some point estimate, which was the sample proportion, 0.887, that's our best guess at what the population proportion might be. And then we built out our interval, right? We said, okay, if I move out 1.96 standard errors from this estimate, I've built a 95% confidence interval. And so our interpretation is going to be, we are 95% confident. So this is the moment of truth. You probably already got it from this general one, right? To check the one that you worked through. We are 95% confident the interval from, what was it? 86.7% to 90.7% captures. Now, here's where it's going to be really important. Often I can find that true population parameter that we're trying to capture in the original question. Now, the problem is, do I have the original question somewhere around here? From the example last day, what a rabbit hole. Let's see if I have it here. I feel like maybe this was the question. Guess I stole it from the textbook. I'm gonna bump these down here. Captures. The thing we're trying to capture is, of course, so compute and interpret a 95% confidence interval for the population proportion. The population proportion of what? Of American adults who supported expanding the role of solar power, right? And so here, population proportion of American adults who supported expanding the role of solar power. So it always has to be about the same group, same population that you pulled your sample from, okay? And so it's going to be talking about the population of the American adults who supported expanding the role of solar power, but we based it off of a sample of 1,000 of those Americans. So here it captures the population proportion of American adults who support expanding the role of solar power. Okay. So I'll kind of show this. Unfortunately, there's a page break right here, so that's going to look weird later, but if you were here, you had to be there. So here, right, I'm going to go back to the question, pull the blurb from the question here, and that's what I want you to do. I'll tell you to build a confidence interval for the population proportion of mice in a field. I don't know, whatever. Or something boring like American adults supported expanding the role of solar power. No, that's not boring, but it's long. So here, this information comes from the question. Guess I shouldn't point at the 1,000 there. Yeah. Good. It's a long review from last day, but it is going to be really, really important that we have a good handle on how to build confidence intervals. That's not so bad, right? There's like hardly any math here. That's everyone's kind of major realization with stats. So they come into statistics thinking, oh, I'm not good at math, and well, that's garbage. But a lot of people feel that way, right? Everyone can be good at math. Oh, I'm not good at math. I'm not good at math. And then they're like, oh, the math is actually fine. Yeah, that's okay. And then some people are really disappointed. Hey, there's no math here. I know. It's all words. It's all interpretations and reading questions carefully. Math is fine. Yeah, but so it's kind of funny to see those two groups in the same course, because usually that's how it is. And there's this one group who's thrilled that there's no math, and then there's the other group that is feeling like they're being cheated out of the math. But there's more math that we could do, but not in this course. Okay, so I guess that's kind of the end of our review. Wow, that's a long review. So the next thing that I want to talk about is just going back to the confidence interval. We didn't really talk about the margin of error, but in a confidence interval, we have a point estimate plus minus the critical value of Z star, or just abstract linear algebra. Abstract anything is not fun. As soon as it had the word abstract in it, unless I had to take it, I was like, oh, no, you learned that lesson the hard way. So the point estimate, some people like it, but no. And you go into it because linear algebra was so fun, right? And then hopes and dreams crushed. If you haven't taken linear algebra, it is really, really fun. I think it's like math 221 or something. But anyways, that's enough about that. Selling other courses, come on. So the point estimate, plus minus some critical value, and then the standard error of the point estimate. Maybe I'll just write PE. That's weird. But I think you get the idea. So now this plus minus part, we call it the margin of error. And you might have heard that term before, right? Because in a lot of reports, all we do is report the margin of error, which is the critical value multiplied by the standard error already, right? And so so a lot of the time we just report the margin of error. We don't report the critical value as well as the standard error. So this portion is called the margin of error. And I'll bump this down even more. And so the margin of error, we're going to come back to it, right? But it's really important that we know that that's that plus minus chunk. It's basically the buffer, as I call it. So often a report will only include the margin of error. If you have a small margin of error, what does that mean? Well, the Z star is going to be the same, right? For a 95% confidence interval, let's say, right? So for a 95% confidence interval, Z star is going to be 1.96. It doesn't matter what else is going on there. Well, the only way that we can decrease the margin of error is if we decrease the standard error, right? And so if we have a small margin of error, it means we have a small standard error, okay? And that means that we have a more precise estimate, right? Because we were able to get really close to that point estimate. So often we're trying to minimize the margin of error, right? We're trying to minimize how wide our bounds have to be around the estimate, right? And so if you want to show off how strong your data is, then you're going to have a low margin of error, right? Depends on what you're talking about too, right? What is low? So some populations, you'll never get a margin of error that's less than 10% just because there is so much variability in there. And then some populations, a margin of error of 3% might still be really large, right? So it depends on the population that you're talking about. But if we assume a 95% confidence interval, a 95% confidence interval for one sample proportion, because that's all we've introduced so far, right? So for one sample proportion, which is p hat, oops, that doesn't look like a hat there. So if we assume a 95% confidence interval for one sample proportion, then Z star will be 1.96, right? For all margins of error, right? So for any margin of error. The only way to decrease the margin of error, right, is to decrease the standard error. The only way to decrease the margin of error, which usually I just abbreviate ME, but a lot of fields like to use MOE, but I mean, technically, I think acronyms shouldn't include the of, but whatever. So that's why I use ME, but doesn't matter. So here I'll define it, margin of error, which I use ME or M. I know they use a capital O and it just drives me nuts. But anyways, personal quirks, I guess. So the only way to decrease the margin of error, right, is to decrease the standard error. Now, for one sample proportion, the standard error of p hat, we said was what? P hat times 1 minus p hat divided by n. P hat is what it is. The only way that I can change this thing is by increasing the sample size. Right? And so we decrease, this is where it gets complicated, right? Because n is in the denominator. So if I increase n, then I'm dividing by a larger number. And so in turn, this thing is going to decrease, right? So we decrease the standard error. I'll specify of p hat by increasing the sample size, which is n. Right, and so it's kind of this chain of events. So the only way that I can decrease the margin of error is by increasing the sample size, right, to get a more precise estimate around the point estimate. Okay, so that's just something to keep in mind, and we'll come back to it, but we have to introduce a couple of other concepts before we come back to it. But what happens and where we're going to end up eventually is if we have some desired margin of error, we're going to be able to calculate what sample size would I need to make that happen. Like I said, there's a couple of other things that we need to introduce, but that's one of the things that we'll be able to do, right? If I tell you, okay, you want to have a margin of error of 3%, right? What sample size are you going to need? And you'll be able to calculate that. And you can probably put it together here. It's just that the problem becomes that we don't have a sample proportion because we, in theory, haven't collected a sample yet. So we need to kind of deal with that, but we will get there. Okay, so now that's kind of, we're not going to leave confidence intervals. They're going to haunt us for the rest of the term, but I want to introduce hypothesis testing. Now, this is going to be kind of a nice slow introduction to hypothesis testing. And so, and honestly, I think the textbook does a really nice job of introducing it. And so if, you know, what we're doing here doesn't quite make sense, then I encourage you to read section 5.3, maybe all of chapter 5, doesn't hurt. They're pretty short, so, or I don't know, maybe because I know what they're gonna say. I'm like, oh yeah. But yeah, it won't hurt to have other examples thrown at you. I've made an effort to not use the same examples that they have, just so you have more to look at. Okay, so let's see here. I'll start this on a new page. You know what? I'm going to keep these here, my little scrolled away examples that I'll pull in a little bit here. But so section 5.3 is on hypothesis testing. Finally, for some of you, I know I've been waiting patiently. Finally. Not quite at p-values yet, but we will get there. And don't worry, there's tons of fun memes for p-values. So I'll see if I can bring some in, but a lot of fun memes for a lot of these things. I need to do a better job of bringing them in. Okay, so for hypothesis testing, one thing that I want to mention is it can get really, really boggy. Okay, there's a lot of ins and outs that we need to keep track of. And so what I want to do is just give you a quick overview of everything, and then rest assured, it's basically all we're going to be doing is confidence intervals and hypothesis testing here in chapter 5, and then in chapter 6, and then in chapter 7. And then if we wanted to, we could keep doing it in chapter 8, but then we kind of change gears. So, and we focus on other stuff, but we can keep doing it for basically any scenario that we would want to look at. And so here we're laying the groundwork. It's not supposed to make sense necessarily the first time around or the second time around or even the third time around. But as you go through it and kind of go through the motions, I think what you'll find is that pieces will start falling into place. So the only thing that I'm trying to say here is stick with it, right? Keep working through problems and just kind of eventually things will start falling into place, but do not expect it to make sense right away. Okay, so hypothesis testing. We're going to start by bringing back the confidence interval, right? And so we can do hypothesis testing. It's kind of new age, I guess. We can do hypothesis testing with confidence intervals. There are some drawbacks, and so I'll introduce it with a confidence interval, and then we'll go and we'll do a formal hypothesis test probably tomorrow, mañana. Okay, so I want to go through and very vaguely list the steps of hypothesis testing. Okay, so the first step, the steps of hypothesis testing or HT is usually how I abbreviate it. So the steps of hypothesis testing will be the same for any scenario, right? So for any type of data that we want to analyze. So the steps of hypothesis testing will always be the same for any type of data we want to analyze. Now, hypothesis testing is when we have a hypothesis, and I'm sure in, I think, high school science, we have this general science course. It's weird, but now that I think about it, I'm like, weird. Science 9. It's everything. But you probably had to come up with a hypothesis, and something simple like, does water boil when I heat it up, right? Yes or no, right? And so your hypothesis is that when I boil water, or when I heat up water, it'll boil, it'll come to a boil. And then your other hypothesis is that it doesn't, right? And so we have this idea of hypothesis testing already, but we don't have the official formal framework typically, right? We just kind of do it once, and if you thought what would happen happened, then you're good with that. That's not really how it's going to go, right? You're going to need support from data, right? And so how we do it depends on the type of data that you have, but we're going to start by focusing on just one sample proportion. Okay. And so we will start by focusing on one sample proportion, which is our p hat. It's the only thing we've talked about, but it provides us a nice kind of jumping off point for all these skills. Okay, I got skills, I got mad skills. So, got a chuckle. So the steps for hypothesis testing, they're a little bit long, right? But we do hypothesis testing when we have some idea, when we have some theory about our data, or potentially our population, or ideally our population. And so, and maybe I'll put it in green. We conduct hypothesis testing when we have I don't want to say an idea, and I don't want to use the word hypothesis, right? But when we have a theory, I'll say, a theory or hypothesis, but that seems kind of weird to introduce, what is hypothesis testing by using the word hypothesis. But a hypothesis is just a theory. It's this kind of thing that you want to know if it's true or not, or kind of within reason. When we have a theory or hypothesis, if you're comfortable with that word, you will be, but maybe not right now. When we have a theory or hypothesis about a population parameter, the word population here is optional because parameter is a measurement from the population. So it's pretty redundant to say population here. Okay. We'll put it in brackets, but I like saying population parameter, even though it's redundant, because it just emphasizes that, hey, we have this idea about how the entire population might behave, right? And so we conduct hypothesis testing when we have this theory about a parameter, and we need formal testing as proof, either for or against our theory. And we need formal testing using data to provide evidence either for or against, our theory. So pretty big, but that's the idea, right? We have some idea that we want to check, and we need some formal testing that we can do. We can use confidence intervals to introduce the steps of a hypothesis test. Okay, and so just to give you a heads up, right? We're going to start with confidence intervals, and then we're going to make it more formal using what we call p-values. So we will introduce both, but because we've seen confidence intervals, that feels like a good place to start. And so we can conduct hypothesis tests with confidence intervals, and later we will introduce the more formal p-values. And later we will introduce the more formal p-values. Yeah. Okay, so what are these steps? Okay. Remember, I said the steps of hypothesis testing will always be the same. So what are these steps? Now, we can break these up into like 7 steps if we want to, even 8 steps if we really want to. I like to stick to 4 steps because it's a nice kind of number of steps to have to remember before it gets too boggy. Although the last step is really quite long, it's about 3 steps long, but at least how my brain works is I like to have 4 things that I need to remember to do in order, and they'll start falling into place, right? You're not going to need to memorize these steps, but we'll introduce them. So you have something to work off of. But so the steps for hypothesis testing, like I said, are always going to be the same. Now, we're going to do a run through of all the steps, very few of these steps are going to mean anything until we go into more detail about them. All right, but step number 1 is to state your null and alternative hypotheses. And I'll leave it there, but then I want to talk more about each of the steps kind of in detail, but it helps to have an overview of what we're doing. So we want to state the null, the null and alternative hypotheses. Step 2 is going to be do the test. Now that doesn't really mean anything. And in our case, it would be build a confidence interval. So I'll start with build a confidence interval, or later do the test, which really means calculate the test statistic. We haven't introduced any of that, but I want to have it here so that when you go back, you can kind of see it when you know what a test statistic is. So calculate the test statistic. Step 3, if we have built an interval, then we look at the, consider the null hypothesis against the interval. Of course, that makes no sense right now. That's okay. So compare the null hypothesis, or maybe I'll say why not? I'm introducing all kinds of things that you don't necessarily know. Compare the null value to the confidence interval. Hey, why is my pen doing this? There. Or find the p-value. Find the p-value using the test statistic. Right, kind of depends on if you're doing it with a formal p-value approach, but there is this kind of connection, and they're going to be basically doing the same thing. And then our final step is to state the conclusion. Now, the conclusion is going to have multiple parts, but for now, I'm just going to say state the conclusion. Okay. So now I want to go into more detail about each of these steps, specifically for using a confidence interval to do this hypothesis test. So put it on a new page here. Step 1, state the null and alternative hypotheses. This can be really difficult, okay? And part of the, I would maybe argue even that it's the hardest part of all of this is stating your null and alternative hypotheses, because it involves identifying what type of data you have, right? So what null hypothesis is going to be appropriate. And then once you've decided that, then you're going to have a clear path to how you're going to do this hypothesis test. And so stating the null and alternative hypothesis is going to take a lot of work and picking it out. And there's some key things that we want to include. So the null hypothesis is denoted by H subscript 0. Okay, this is called H naught. So you could call it H null, but everyone calls it H naught because null and naught are both 0. Okay, and so this is called H naught. Okay, maybe I'll make this subscript 0 a little clearer. Okay, and then the alternative hypothesis, you can denote it by HA, lowercase a, capital A, or 1. It depends on what you like. I like a capital A because, I don't know, they just look cleaner. But the alternative hypothesis, I guess singular, hypothesis is denoted by HA or H lowercase a, or if you prefer H1, any one of those will work. Okay, and that's not too bad. And the main thing to remember about these hypotheses is that they are statements. So we could make all our statements about our hypotheses in words, right? So we could say my null hypothesis is always going to be a statement of no change. Okay, and so and then the alternative hypothesis is if we have enough evidence, then we can go for the alternative hypothesis. But the null hypothesis will always be a statement of no change. And in general, these are statements. Okay. And so H naught and HA are statements. Okay. And specifically, H naught will always be a statement of no change. Okay. More specifically, H naught will always be a statement of no change. Yeah. So if we think back to that little science experiment that we were doing, right? If I boil water, or if I heat up water, I should say, then the water will boil, right? The statement of no change is going to be if I heat up water, it doesn't boil, right? So in that case, it's kind of a weird situation because it has to be the statement of no change. So for example, in a Science 9 experiment, we suspect, and I don't know why I made it Science 9. I just feel like that's when we did these things. I can't remember. I had Mr. Farah, I think. Anyways, and he was like this really loud guy, and I remember him talking about boiling water. Anyways, here we are, Science 9. So in a Science 9 experiment, we suspect that when we heat up water, it will boil. We suspect that when we heat up water, it will boil, right? Assuming that it goes to the appropriate temperatures, blah, blah, blah. Right, and so the statement of no change here is going to be, if I heat up water, it doesn't boil, right? It stays the same. And so H naught is a statement of no change. Yeah. So in this case, H naught is a statement. So I use a colon because it's a statement, right? And I want to highlight that. Okay. Okay. So it's a colon because it's a statement. And so H naught says that if I heat up water, the state will remain the same, right? It will not boil. If I heat up water, it will not boil. Okay. That's a statement of no change. So that's the key in keeping kind of these H naught HAs straight, is that the null hypothesis is often not the one that you think is going to happen, right? But it's the one that you have to start out assuming. And so our go-to example is, of course, you're innocent until proven guilty, right? And so you're innocent until you have proof that they're guilty, right? And so it's the same sort of situation. So if I heat up water, I have to start out and assume that it's not going to boil until I have proof, right? I did it 40 times and it boiled every time. So now I feel confident saying, yes, it's going to boil, right? So then my alternative hypothesis is also a statement. So notice, don't worry, yeah, we do. I've got a pretty funny meme about that. So yeah, this looks like another word, right? So Santa Claus, let's say, right? And so don't worry, there's tons of memes about that. So, and I've got the best one, but I'm saving it for the best time. So the alternative hypothesis is, of course, another statement. And so now I have to be talking about heating up water, and I have to be talking about whether it boils or not, right? But I've already covered the not boiling section here. And so here, my statement would be, if I heat up water, it will boil, right? If I heat up water, it will boil. Okay. Now, this is obviously a very basic example, but the idea stays the same, right? And so I'm going to have some idea about the population proportion, and then I use my sample proportion to either support or go against that idea. Okay, so our null hypothesis in general, we're going to have a null hypothesis, which is going to be a statement, and it's going to be a statement about a parameter. Okay. Our options so far for parameters is going to be just P, which is the population proportion, or later we'll move into mu, which is the population mean, right? The statement of no change has to be an equal sign, right? And so that's always going to be the case. So the null hypothesis will always have an equal sign in it. Now we can adjust this equal sign. It can be less than or equal to, greater than or equal to, but for simplicity's sake, I'm just going to have just an equal sign here. Okay. And so just as a rule, I'm going to have equal to, but as long as you have the equality in the null hypothesis, then you're fine. So we're going to have a statement that says that the parameter that we're interested in, for now, that's going to be P, the population proportion, is equal to some value. Now that value is going to be called the null parameter. Sorry, the null value. I don't know, reading two words at once. And so this is going to be the null value. Okay. Because it's in the null hypothesis and it's the value that I want to compare my my parameter to. Okay. So then what happens with the alternative hypothesis, just like up here, when if I heat water, it will not boil. If I heat up water, it will boil. I have to keep talking about the same thing. The only difference is going to be in the equality. For now, I'll have the opposite for the equality. Let's start there. So I'm going to have a not equal to. Later on, what we'll do is we'll look at less than or greater than if we're concerned with a certain direction. But for now, and as a default, we use not equal to. All right, so our options are either our null hypothesis is one of no change, so an equality, and then our alternative is going to be not equal to. But then, of course, the things we talk about here have to be the same, right? So once you've decided, once you've built up your null hypothesis, that's the hardest part. And then you just take that information and you replicate it down here, right? And I'm using, is this a ditto sign, or I can't remember what it's called, but anyways, it's just saying repeat what's above, right? And so I'm using that for emphasis because these have to be the same values that I'm talking about. For example, if your null hypothesis is about apples, then your alternative hypothesis can't be about oranges all of a sudden. That makes no sense. You don't want to do that. Right? And so here, these values must be the same in both hypotheses. Yeah. So that's in general. How about we look at just a one sample proportion scenario? In a one sample proportion scenario, we're going to have a null hypothesis. It has to be about a parameter, right? And in the one sample proportion scenario, then the parameter is going to be P. And I know I have to have an equal sign in here, equals. And then the null value, how I show the null value is I'm going to have some value here, but as a placeholder, P naught. Okay, so that's what makes it the null value. Now this P naught is the value we want to compare the sample proportion to. The sample proportion to. So once we've decided that our null hypothesis is that P equals some P naught, where that's going to be a value, okay, then we basically have everything that we need to write out the alternative hypothesis, which is going to be HA is that P is not equal to that P naught, that same P naught, the same null value. Okay. And maybe I'll put a little note here. P naught is the null value. Okay. Got a lot of circles here. This, this, this. Okay, this. All right. So that's going to be our layout for setting up our null and alternative hypotheses. Now, that's easier said than done, right? But let's see here. Let's bring in, where did I? Oh, I put it above. Well, that was a while ago. Eek. So I've got this example that I want us to work through. And just because while I remember here, we might not use it, but I just want to have it kind of available. We might not get to that point yet. Okay, things have stabilized here. Oh, I see now that I've cut off the actual question, but so example 4 doesn't have anything to do with us, but just cross that out. According to a 2012 Bank of Montreal RRSP study of 1,000 Canadians 18 years of age or older, 67% of Canadians have a registered RRSP, registered retirement savings plan. I just skipped to RRSP. A StatsCan study reported that in 1999, 57% of Canadians had an RRSP. The follow-up question would read something like this. Is there evidence? Now that is there evidence is a clear indicator that you're going to have to do a hypothesis test. Okay, so is there evidence? Is there evidence that the proportion of Canadians who have an RRSP has changed since 1999? Has changed since 1999. So this portion here, is there evidence? That tells me that if I'm asking for evidence, then that's a clear way of saying do a hypothesis test. Okay. This means we have to do a da. We're Russian all of a sudden. This means we have to do a hypothesis test. Eee. We've only got the tools to set up our hypotheses, but that's going to be the hardest part, like I said. So, like the Russian, huh? What is our null hypothesis in this case? So we've got this information. Now it's really important that we keep track of our sample information versus our hypothesized value. They'll both be in there, right? And so we just need to keep track of what's what. And so I always find that it's useful if we pick apart all the information that we've been given, right? And so here, for example, I have 1,000 Canadians 18 years of age or older. And so this defines the population, right? Canadians 18 years of older or older. So our sample size N is 1,000. Okay. Our population how can I do this? How can I pull this off? Whee! So the population that we sampled from is Canadians 18 years of age or older. 18 years of age or older. We could just call this Canadian adults or Canadian adults. If you want to simplify things a little bit, right? So I should have said Canadian adults, and I should clean that up just because I can. Because it doesn't help when I'm sloppy, because I know what's going on, but you guys have to read back on this potentially and make sense of it. Okay, so we've identified our sample size, our population, and so from the study, we find that 67% of Canadians have an RRSP, right? And so this here is what? This is going to be our sample proportion. So I'll try to bring that up here. P hat is 67%, but you know what? I'm just going to go straight to the decimal, 0.67. Okay. So the value that we want to compare our sample proportion to, so remember here, the value we want to compare the sample proportion to is this 57%, okay? And that's what makes this 57% the null value. P naught is 0.57. So what I want you to do is we'll pick this up tomorrow morning. And what I want you to do until then is set up your null and alternative hypotheses, and then we'll pick it up from there. Okay, so tomorrow I'll just start with this block and we'll just keep working at it. Okay, if you want to, you can try building your confidence interval for P hat, see what you get, okay, and maybe try it out. But I'm pretty much out of time, and this is a good place to stop. So if you have any questions, let me know. Otherwise, I'll see you tomorrow. Stop this.